Alright, Calc 3, this is the second part of those 8.2 notes. We were doing surface integrals, so we're going to do those with parametric now. Last video we did it with implicit, so you had to do the all the stuff for d sigma, n, and all that. So n is just the gradient over its magnitude, and then d sigma was what it was before. The magnitude over the dot product of gradient of f and p. So now we're doing it with the stuff we did at the beginning of this chapter, which was we parametrized surfaces and found the surface area with those. We can now find surface integrals with them. It's very similar. So the first problem is, well, first of all, write down the formula. Basically, the only thing new to the formula is this piece right here, the g of all of this. That's the new function that has to be within the two variables. Okay, and then d sigma is the same as it was when we did parametric surface area. It's just the magnitude of the cross product of the partial derivatives of your parametrized surface, and then du dv, or whatever the variables are. Alright, so let's look at number 4 here on this note sheet. We're integrating this big function g of xyz equals x squared over the cone z equals x squared plus y squared, where z is between 0 and 1. Now, this is the exact same problem from 8.1 notes. Okay, so we actually found some of this information out when we did the 8.1 notes. So when we did the 8.1 notes, we wrote this in terms of r and theta. So we wrote our surface as r comma theta of, it was r cosine theta because that's what x is equal to, r sine theta. And then z is equal to this, which is just r, remember? And then we got that the bounds for both of these were 0 to 1 for r, and for theta, it was 0 to 2 pi, because the cone's going all the way around. Now the only other, and we also found the magnitude of the cross product, so we're going to skip doing a cross product for this problem because we don't need to. We did this on the other note sheet. We found that the magnitude of the cross product of the partial derivatives of that function there is r root 2 was what we got. Okay, so now we're going to do the surface integral using this formula. So what happens here is these are all things that we did last time. So that's last time. So now the integrating this function, I'm sorry, that wasn't supposed to happen, is equal to the double integral over the surface. G of xyz is equal to x squared, and then we have d sigma. Well, again, we need to be everything needs to be in terms of the two variables that we're working with, which are r and theta. So we also have to convert x squared. So x squared becomes r cosine theta squared, which is r squared cosine squared theta. So I'll put that in parentheses. Our bounds for r are 0 to 1. Our bounds for theta are 0 to 2 pi. We now also need to put d sigma. Well, d sigma is just the magnitude of the cross product times, again, dr d theta in this case. So we're going to be putting the r root 2 dr d theta. Notice how we have really an r cubed here, because really, remember, we're going to be integrating the r first. So pretend we have an r cubed, a root 2, and a cosine squared theta. We don't really care about the root 2. We'll pull that one out. So the root 2 will be out here. I still have my bounds from 0 to 2 pi. If I integrate r cubed, I get r to the 4th over 4. I have to evaluate that from 0 to 1. Okay, so I accidentally stopped my recording but kept talking. So what I did basically was we still have the cosine squared theta d theta. So we're not going to worry about that right now. We're going to evaluate the r to the 4th over 4 from 0 to 1, and we get 1/4. So I have the 1/4 and the root 2. I put that outside, so now I'm down here on this next line. The 1/4 came out with the root 2, and now I write my integral. My integral is from 0 to 2 pi. Remember, cosine squared has the identity of 1/2 plus cosine of 2 theta over 2 d theta. Okay? If you need to pause the screen briefly to write that all down, I don't know why it stopped, so we'll figure it out later. But hopefully this is working again. So now we integrate. We have this out here. We have this inside. evaluating this from 0 to 2 pi. Okay? So when we put 2 pi in, we get pi. 2 pi will be a 4 pi, that'll be a 0. So we get root 2 over 4 times pi plus 0 minus 0 plus, again, 0. So basically this is pi root 2 over 4. Okay? So that's how you do a surface integral with parametric equations. So let's do one more problem. We're going to do the flux. So the rate of the fluid flow of F outward through a parabolic cylinder. That's going to be this problem right here that I'm scrolling down to. Here we go. So first thing we have to remember is that flux is equal to the integral over the surface of F dot N d sigma. Okay, so we need to get all three of these things. Since we're going to be doing this with parametrics, we have to find what R is. So in general terms, we always make R in terms of X, Y, and Z, and then we start playing around with it and changing it. Sometimes we make X R cosine theta, Y R sine theta, and then we do the polar. Sometimes we can leave it as is and we have to eliminate one variable. Well, this is actually very easy to leave as is, because if you notice, it tells you the parabolic cylinder is y equals x squared, which means we can do the substitution for y and make it x squared. And when we do that, we only have two variables. So that's my parametric equation. It's also nice because I also give you the bounds for the two variables that we want to have it in terms of. So I get R is equal to x squared now, and then z. Okay. So I need to find my two partial derivatives. Rx is equal to 1, 2x, and 0. Rz is equal to 0, 0, 1. Okay, so now we need to find a few things. We need to find n. Remember, the normal vector is either the gradient over its magnitude or the cross product over its magnitude, because again, it's a unit vector, and if we want a vector normal to the surface, it either has to be a cross product to get there or we use the gradient. Those are both ways to get a normal vector. So when we do parametrized surfaces, we use this formula. Well, in this case, it's going to have x's and z's. Okay. So we need to find the cross product is what I'm getting at here. So let's do that next. So I get Rx cross Rz equals I, J, K, I, J. I'm going to go kind of fast here because of time. Again, if you need me to slow down, just pause the video. It's much better than in class when you just have to yell, hey, stop talking. Hope everyone's doing well, by the way. This is the first video that we're doing since we found out we're not going to be back in school, and I'm very upset about that, but, you know, we can't change what's happening right now, so we got to keep going. Alright, so we get that the cross product is equal to 2x in the I, nothing in the j, nothing in the k, minus nothing, nothing, minus j. Okay, so if I write that in my other form, it's 2x negative 1 comma 0 is my cross product. Okay, so that means my normal vector, I'm going to bring that back to here. My normal vector becomes the vector 2x negative 1, 0 over the magnitude of this is when you take the square root of the squared pieces. That becomes 4x squared. And negative 1 squared is a positive 1. You cannot simplify that, we leave it as is. So there's my normal vector. I have my normal vector, great. We now need to get f in terms of only x and z. So if we look up here, f is now in terms of all three letters, so we have to put an x squared here. Okay? So what happens is we get f is equal to, instead of y, it's x squared z, x negative z squared. So now f is in terms of the variables we want. If we get f dot n, let's do that next, because that's part of our flux equation. That's taking these two things together. Remember, when you're doing a dot product, just work with the vectors. You don't have to worry about that magnitude on the bottom yet. We'll just leave it as is. So when I do the dot product of these two, I multiply this times this, so I get 2x cubed z. Then I get x times -1, which is minus x. Then I get this times 0, which is 0. So that is my dot product. Oh, but we have to remember, we still do have the bottom. You don't have to do anything with it right now. Okay, so there's f dot n. All we need now is d sigma. Well, remember, for parametric surfaces, d sigma is just the magnitude of the cross product and then the two variables. So in this case, it'll be dx dz. Well, we already know what this is, so we can write out our final flux integral and say that flux is equal to the integral of 0 to 1 for x, 0 to 4 for z. We have f dot n here, so that's 2x cubed z minus x all over the magnitude of that. What's great about this is you'll see in a second. And then we have to multiply it by d sigma. Well, d sigma is the magnitude of the cross product. Well, that happens to be this again. So they will actually cancel out. Because remember, this is d sigma, and then this is f dot n. So finally, we get a flux integral of 0 to 1 and 0 to 4 of 2x cubed z minus x. And that's evaluated from 0 to 1 and 0 to 4 dx dz. So that will be my flux integral. I'm going to stop here because the video is long enough. You guys should be able to integrate that. Do x first, then do z. Very simple numbers. I just wanted to go through how to get that information. So that is how you do flux and how you do a surface integral with parametric surfaces. Alright, that should do it for this section. All we've got left are Stokes' theorem and the divergence theorem. So I will get you guys some problems for the rest of the week, and maybe we'll start up Stokes' theorem at the end of the week. Have a good rest of your day.